my great pleasure to introduce Wolfgang Wahlster, my colleague from the DFKI. Wolfgang is the CEO and managing director and one of the founding directors. In fact, I think the two of us, we did that 25 years ago to, no, 30, Wolfgang. 25. All right. 25 years ago, the DFKI, it's one of the largest, in fact, I think by now it's really the largest AI institute worldwide. Wolfgang has received many honors over the time, multiple doctorships, all sorts of awards. You better look up the web page. There is a very long list, Wolfgang. I don't even remember them all. Wolfgang's background is in computational linguistics, our first area within the DFKI, and then he moved to human-computer interfaces, and now he has one of the largest departments, apart from being the CEO in the DFKI as well. Wolfgang, I think.
Yeah, thank you very much, Jörg, for the kind introduction. Thank you also for inviting me to this conference. And today I want to address a topic which is very specific, I think, for research in Germany right now. It's about situated learning and assistance technologies for Industry 4.0. I'm a member of the so-called research union of our government, and I'm the chief advisor of our chancellor for ICT, and we discussed a lot where can we make a difference in ICT research and how is it related to economy in Germany. And let me start with the basic motivation for going into this area. As you may know, in industrial production is really the backbone of Germany's economic performance. We have about 7.7 million jobs directly in production, but still 7.1 which are related indirectly to the production business, so that actually every second job in Germany still depends on industry. This is of course not the case in many neighboring countries. If you look at the UK and other countries, they are de-industrialized. They are more keen on service or financial engineering. This was not the case in Germany, and I think in the end, economically, it was good. Last year, we had still a trade surplus of 158 billion euro in industrial products, especially machine tool industry and automotive industry. But of course, there is a lot of challenging stuff going on worldwide. So that's the idea, that we try to start the next industrial revolution to be again ahead. And this industrial revolution is now driven by the future internet. The key idea behind this that in the next generation of factories in Germany, we want to have systems which are all IP, that everything is based on internet protocol. This is not the case right now. If you go to a factory today, there are many so-called field buses. Actually, there's a chaos of such field buses. Up to 100 such field buses are used. M2M communication, machine-to-machine communication in a wireless way is very important. The embedded digital product memory will change in a disruptive way the logic of production, because now every single item has a small memory, and this memory tells the product what kind of services are needed to actually manufacturing this product. This means that we can have a completely new paradigm, kind of completely distributed, like we did, for instance, in AI with multi-agent systems, so that actually every single product requests certain services. I will come to this later in connection with the learning. Third, we are very keen, of course, on resource efficient production. Green production in Germany is a big issue, and so-called urban production. We want to have the factories back in the cities. Actually, just 1 month ago, a new factory was opened in Stuttgart in the middle of a neighborship where only private people are living in their home. this would be impossible in the 20 years ago. It was possible, as we know, at the turn between in the 1900s. When you went to Berlin, for instance, you saw all the factories in the middle of the town. This was, of course, very bad because of all the pollution. But on the other hand, today, when you have a clean manufacturing, you want to move this back into the city. Why? Because you save a lot of CO2 when people go back and forth between the factory and their home. Here in Stuttgart, people can actually, the workers can walk or bike to their working place in the factory. And last, I think the revolution we see right now with software configuration of systems also goes into the factories and also in the cars. Of course, Germany and Europe in general is not very good in the app business. You know, the platforms are owned either by American companies like with the iPad, the iPhone, or Korean companies or Japanese. But we will do the same app configuration of machining tools, I will show you in this talk, and also for cars. BMW has opened the first app store for car tuning. So what does this mean? Germany is now preparing for the fourth industrial revolution based on the Internet of Things, cyber-physical production systems, and the Internet of Services. So in this talk, I want to show the consequences for learning technologies in the context of Industry 4.0. Cyber-physical systems are being used in the smart factory. I will talk about mobile and location-based so-called in-situ learning in the smart factories. I will show you some of our work about augmented reality tutorials for the installation, maintenance, and repair of industrial equipment, crowdsourcing for mobile repair tutorials on smartphones, and finally, some things which are not directly related to Industry 4.0, but which show this paradigm of tangible interaction. I think it's very important, of course, in the factory to have you deal with real physical objects, and you should use this context, of course, for in situ learning. And then finally, also on-demand web retrieval. If you have internet connectivity everywhere, you can exploit this, of course, and then I will conclude. Now, one of the key issues in computer science today, as we all know, is that we have already started 10 years ago to go into the era of post-PC. That means the paradigm of personal computing is now fading out. We all know this. We are already in the era where we have many computers for one single users. Here, the guys sitting there have 4 or 5 computers I see in front of them, and they have more in their cell phones and so on. And again, Europe and especially Germany is very strong in embedded computers. Not so, as we all know, not in smartphones, not in notebooks, but embedded computers. And 90% of all the computers are actually embedded, especially again in machining tools for factories. This is a very strong market, so the idea was, why not have complete intelligent environments in the factory? So not only the single machine, but the whole factory becomes an intelligent environment with many sensors and equipment. Now, when we talk about the Industrial Revolution, as you know, all of us remember in textbooks about history of industry, the first was when the mechanical loom was introduced. This was mechanical production. Of course, when you look from this from the learning perspective, not much had to be learned, because actually the factory workers, and this was the pity about this, did always the same. Maybe their lifetime, they learned once, yeah, let's say 2 months, and then for the rest of their life, they always did the same stuff. There was not a lot new knowledge to be gained. It was very monotonic. And then the second revolution, which was Taylorism, we all know that also very simple products like the first cars by Ford, they all had the same color, the same size. Actually, only one car was produced. No variation. Again, from the learning perspective, very simple environment. Again, very boring for many people who work there. So not a big issue. How can we learn? Third revolution, this is what is going on since a couple of, let's say, 50 years, where IT was already introduced, electronics. There were heavy robots starting to work. There was more to learn, but still there was a clear division between physical work and the more cognitive work, and this is now fading away. The complexity goes up with every revolution, and now in the new revolution, the understanding of IT, of Internet of Things, of cyber-physical systems is really key. That's the first thing. Second, the production cycle is getting so short that people who work in production have to learn more or less every week new handling procedures, new maintenance procedures. So the learning issue really becomes a key to the success of production in the fourth industrial revolution. It's one of the main issues, and we discussed this a lot with the government. We started a program which is quite big, 500 million euros, not from the European Commission, but from the German government for this program. And the learning is one, learning technologies for factory workers and engineers of the future is one of the key elements of this program. From the paradigm of computer science, we see the development from embedded systems over networked embedded systems, now to what we call cyber-physical systems. The cyber-physical systems, that's the core of this new revolution. What is a cyber-physical system? I tried to visualize this here very simply. Cyber-physical systems are heavily based first on sensors, so as we have on our smartphones, there are a lot of sensors, so the whole behavior of such a cyber-physical system is based on sensoric input, for instance, in this case, as I show here, location. Second, every cyber-physical system is, of course, connected to the internet, so we have wireless internet all over. So machine-to-machine communication is another key ingredient. We can efficiently reconfigure the cyber-physical systems to show new behavior. You saw it here. When this small box is such a cyber-physical system, it has sensors, it knows where it is, it knows its neighbors. And you see, every node computes a certain result depending on the position of this piece. This is typical for cyber-physical systems. Now, when we start such a factory, first of all, we will have smart materials. So even the materials which go into the factory have smartness. They are software-based. Apps are running on the material. We have the smart factory, which is based on cyber-physical systems, as I explained, has an app platform. And even the products which come out of these factories are, again, smart products in the sense that you can use software to reconfigure them, to adapt them to the user. So Internet of Things on the one hand side and Internet of Services are key elements. And as I said, such a factory in the future will allow us green production, resource efficiency, because the cyber-physical systems also control their own environment and try to optimize resource use. And the same holds with urban production, as I already explained. Now, let's come to the main issue, learning here. Now, as I said, because there is so much flexibility in manufacturing of the future based on these systems, and the variation of the product is so large that actually today we speak already about unique products being produced. If you go, for instance, to a BMW factory, every single car which comes from the conveyor belt is a unique item. There is no second car which will have the same property. The next car coming from the belt is already different. Why? Not only because the customer can order more than 10 million different variants of the same car, but this is not the reason. Another reason, and this is the key reason, is because in such a car there are more than 100 embedded computers, and all these computers, of course, have firmware, have software. There are release changes, yeah, every night, so you can be sure with 100 embedded computers that a single piece of, even if you have the same variant, the software will have changed. So it's really producing single items, and this in very high quality. And this means, again, that of course the people who work there, you see here one of our factory girls, learning, they have to constantly learn new processes. And how do we envision this? First, such an interaction in the factory must be multimodal. So all these senses, not only of keyboard and mouse, but all the senses have to be used. First thing. The same for output, situation dependent. Sometimes you can use visualization, sometimes speech, sometimes the system will just send beeping signals and so on. So we have to coordinate this. And of course, the learning must be embedded in an industrial assistance system. It's very important that we can exploit machine learning technology for drafting the content of such learning tutorials in the factory. And of course, this assistance system must be connected to the reality, namely to the cyber-physical production systems, machine monitoring, resource adaptation, as I said. Of course, such an assistance system must be knowledge-based, so we have in our systems knowledge about the workflows, so workflow process models. Of course, the discourse in interaction is stored, the history of the discourse. User modeling, extremely important, because we, as you will see, we have very different types of people working in the factory, from the engineer to the maintenance field, maintenance technician. And of course, we must have an explicit production model to make this work. Now, if you talk about human-centered and cyber-physical system-based assistance, in this talk I will concentrate on mobile, personalized, situation-adaptive tutoring systems, and second, augmented reality or virtual reality, or even what we call dual reality systems for learning in very complex work processes. There are other elements which are done at DFK. My colleagues, for instance, in Bremen, they are working at DFK on physical assistance with so-called exoskeletons, where the workers, have enforced physical power. I will not touch this. Or the question of location-based maintenance and planning assistance. When you replan parts of a factory, then this is very important. But I will concentrate on the two topics which are in red here. Now, from my point of view, when we introduce the next generation of industrial learning and assistance systems, they must be non-intrusive. We cannot allow, because these people have really to have their main focus on their work in the factory, and we cannot have very intrusive, head-mounted display running around with a helmet. This is impossible. It must be lightweight, and it should be not really distract from the main task. Of course, mobility is extremely important. We cannot sit people, in situ learning in a factory in front of a computer screen. The whole learning process must be in a mobile context. They have to go walk through the facilities. Location-based. What they learn must be, of course, dependent on the type of equipment they are in front of. Situated and context adaptive. This includes the location, but also many other effects, like what is the current state of a certain machining tool. personalized, because in German factories we have a lot of immigrants working. So, for instance, language issue, cultural issues even play a certain role, especially in automotive manufacturing. And finally, it should be multimodal, because there should be a free choice of the modality depending again on the context. As I said, the whole idea of Industry 4.0 is, this was my vision when I launched this program. I said it should be what we see in software technology in the business world. SOA, service-oriented architecture, should be translated into the factory in the sense that every machine offers a certain service, and that you envision the factory of the future more as a marketplace where an emerging product is looking for services to be in its final state. Like a human being going to university, looking for courses, services to learn and to get a certain degree. The car, who wants to be a red car, has to find a painting machine which paints red. So that's the idea. You have not a centralized production scheduling system, but it's completely distributed and relies on the Internet of Things. And this also means that we have to move up in the semantic chain. If you have only machine-to-machine communication, maybe wireless, which exchanges bits and bytes, and the machines don't have a machine-understandable semantics of what's going on, this would fail. So over the years, we worked from bits and bytes via functional descriptions, and now, at the end, we already have in our projects, I'm running one project which is called RESCOM, Resource Efficiency by Communicating Objects. In this case, we use already ontology languages. For instance, OWL, the ontology web language, for the interchange of information of these different machines. So it's an ontology-based factory, so to speak. Now, if we talk about adaptation, I think it's very important to remember, and actually I started about, this was before DFKI, the field of user modeling in Maria Laach about 35 years ago with Alfred Kupser. We coined the term and started the first workshop which emerged into a conference, but we still think it's the essence can be captured in very simple words. First, you collect data about a user. You do some user modeling. Today, it's mainly machine learning about this user data. You extract a model, and then in the adaptation phase, you exploit the model to get certain adaptation effects in the learning context. And this can be implicit or explicit. Of course, as I said, in the factory, we need implicit user modeling in the sense that not the user reports about his own properties, but that we observe the actions of the user. And this brings me to the augmented reality stuff, that we try to get information. Yesterday I was at a conference in Berlin, where we discussed how can you extract with biosensors, simple biosensors, again non-intrusive biosensors, the cognitive and the affective states, and evidence, of course, from the context of all these systems. Now, what I proposed to our government is that in Germany, it's not good, and I think in general in Europe, if you try to mimic, the App Store by Apple or the Play Store by Android and launch small apps there, that's not a good business model because we don't own the platform. But what do we own? We own very complex machining tools. Here is an example of a laser welding machine. And of course, these laser welding machines have now also fully powered, general purpose computers inside. And why not introduce, and we have started this with 2 companies now, an app store. Of course, these apps are much more expensive for these machines. You see, for instance, to run this laser machine in a higher precision mode, like you do motor car, tuning with your own car, you have to pay 5,000 euros. You load down the software, and then the machine runs in another mode. Or you want to run the machine in a more energy-saving mode, green mode, again, you can download the app. But what is important for this audience, you also can download specific learning software. How to, when you want to train people with this very complex laser welding machine, you can download apps. Maybe in this case for free, I don't know. You can also download another user interface, maybe for Turkish people who work in the factory. This is all possible. Second, as I said, location-based learning in industrial assistance systems. We already have implemented such systems using very highly precise positioning systems. Of course, we have to know, and this is working in our smart factory in Kaiserslautern, which was set up by my colleague Züke. Here we have a very big industrial test bed where we can go down to a position of about 20 to 30 centimeters, and we know exactly where the guy is with the notebook. And of course, for instance, errors, maintenance information is displayed in such a context-sensitive way. You see here also a worker looking at on a tablet, which is reading automatically the resource information from the different components of this manufacturing plant, so that he can analyze where, for instance, a lot of energy is consumed, or also hydraulic power is consumed, and then help to tune the system. As I said, when we do this, this cannot be only visual. We have to combine all senses for the learning, getting rid of keyboard and mouse in factories. This doesn't make sense. So what we need is graphics, speech in some context, if it's not too much noise in the factory, gesture, facial expression, eye tracking, I will come to this, and very important, physical action. And this is new. I think that we can trace the physical action in the workflow for learning is extremely new. We know that Google Classes, and you have seen maybe the video, you have the class, you see augmented reality. Really? You see here, the subway is closed. The system gives you a new way through the city, and so on. Now, what we have done is the same in the factory context. Again, we are not very good in Germany for consumer applications. So we said, okay, it's much more important to have real stuff being produced. And this is, again, manufacturing. So in an industrial environment, these Google classes can be used together with the tools to have mobile, interactive, situation-aware tutoring of people. As you see here, for instance, close this velvet, remove these tubes with 2 fingers. So all the instructions are given exactly like in the Google Classes example of the navigation in New York City, now in a factory for the factory workers, which, as I have said, have to learn every day new things. What is the purpose? I think the driving force behind this is first demographics. In Europe, and especially again in Germany, we all know we have a lack of factory staff. Right now, more than 50,000 positions are open, especially if it comes to industrial IT. Industrial IT is needed in these factories. So this cannot be classical mechanical engineers, but you have to know a lot about internet, about software, and so on. So there is a lack. Employees 60 plus have to be trained, because we envision that people in the next 10 years, at least in Germany, have to work much longer. We have now 67, but this will go on up to 75 is the prediction, that people are still working in the factories because of the demographic pyramid. Then we also have highly flexible production and very short production cycles, as I said, which lead to fast changes. So these three factors, working much longer in your life, having a lack of workforce with industrial IT experience, and the highly flexible production, these are the key points why we were, so that we have this. Here, my colleague Stricker, with several PhD students, including one extremely good one who won 2 Best Paper Awards, Mr. Peterson, has jumped on this idea, and what you see here is a worker who has to repair, in this case it's a notebook, a new notebook, which has to get a memory intention, and you see on the screen, and we will go more deeply into this later, what he has to do. There is an overlay which, you know, parts of the workflow have to be carried out, and all the instructions are given through the classes. Now, how can we produce? I mean, normally when we talk about augmented reality, and this is also a problem with the Google project, it's a lot of work to generate this overlay and the context. So one of the key problems, as always in learning technologies, how can we fast and inexpensive, in an inexpensive way, generate the tutorials? And one of the best papers was just this year, IEEE, on the Symposium on Mixed and Augmented Reality, where we presented our DFK technology to start with one video example. So only one video has to be produced to extract automatically the workflow, to train automatically classifiers so that a markerless, as we call it in augmented reality, markerless tracking becomes possible. Then of course we have to do one step, but this is easy, to author the augmented reality overlays. I will show you in a minute how this works, and then we have already the result. This is quite challenging because, as I said, it should be markerless. In previous years, people have used specific visual markers. This is not good because you cannot do this in the factory. Freehand gestures must be allowed. Of course, there are a lot of occlusions because the hands, for instance, are moving into the camera. We have a moving camera in many cases because the guy is, as I said, mobile. We have unintentional actions which should be not gathered into the combined with the workflow. We have even erratic motion and a cluttered background in many cases. So how does this work? We first learn a workflow, and this is, please check this, on a single video stream. So we have one video stream in the factory, yeah, about a workflow, and then the system from this single recording learns the segmentation, and you can even, if you have a variant of the workflow, teach this with one more video. And so that's very interesting. So the sequence is automatically divided into actions, yeah, by the visual process, and classificators are trained to recognize this in other settings. Then, as I said, there is some manual work, but we have a lot of tools. You see the toolbox up there, where you can say, okay, do this with this tool, because tool use, of course, in production is also very important and is part of the learning process, which tool in which part of the workflow has to be used. And then the markerless tracking is started, and it's really, here you see how when we look through our systems, through the classes, what the worker really sees. You see all, how he has to open it, turn it around. Then you see the first announcement, now use the screwdriver. Where the screwdriver, in which direction you have to screw. All this is shown in the overlay for the worker. You really see now the picture which is produced in the classes of the worker, and then it's opened. Some new memory block has to be installed here. This is done. Exactly the position is also shown in the overlay, and so on. So I think this is a very good way to train people in the factory. Now, you would say, is this affordable? Is it really inexpensive enough? And we can say yes, because first, as I showed you, the production pipeline is very easy. So you can do this. We tried it with 6, 7 different workflow. We can do this in 1 to 2 days. Yeah? And this is very important, because if you have to ask a company to produce such a tutorial and it lasts half a year and costs a lot of money, then, as I argued, the working process is already changed. Yeah? Because in the factory of the future, we have such a fast turnaround of the production process. Always new elements are added, new machines come in, that this would not would be a waste of money, because once the tutorial is ready, the process is changed. And I think Mr. Zimmermann, Dr. Zimmermann is also involved. I think you can testify that this is one of the big problems in learning in, let's say, in industrial or commercial context anyway. The fast, inexpensive production of the material, because today it's in all jobs more or less the case that the knowledge is changed very, very fast. It's not like in the first industrial revolution, as I said, our grandfather, he has learned once and applied the knowledge for 40 years in the same way. This is no longer possible, therefore this is a big issue. The second good thing is that we can use mass market ICT components. As I said, Google classes, the first ones are still 1,000 euros. They will come down, this is the marketing plan of Google, to 500 euros. This is very cheap for such, 10 years back, such an augmented reality system, you would pay 20, 30,000 euros. Now 500 euro you can afford. This is very important. Then very simple and cheap sensors, like we all know the Kinect is very much in use also in our factory here for gesture recognition. Pads, as I showed, we use a lot of the location sensitive pads, all the sensors in a normal iPad or Samsung pad, everything very cheap. All IP makes it even cheaper in the factory because we don't have special bus systems. Now, another approach which I followed in my own group, which is based on crowdsourcing, is a bit less ambitious from the machine learning point of view. On the other hand, it has another advantage which we cannot include readily in the augmented reality approach, namely that we use and capitalize the social network between the technicians. Here our idea was, and we have implemented this on Android smartphones, that when you run around in the factory, we use NFC chips we have anyway in the factory to mark electronically, with electronic labels, the different parts of the machine, so that the tracking of the workflow is not done by visual means, like in the previous example, but here by just reading on your smartphone. And the new Samsung, for instance, the Galaxy 2 has an NFC, is NFC enabled. So you go along with your smartphone, a smartphone actually recognizes whether you are very close, because it's near field communication to a certain device in the factory. The navigation through the tutorial is done by manual workflow following. We automatically identify the parts with NFC tags, and then the new thing here is that, again, it's multimodal in situ tutorial, but you as a technician can augment this tutorial by your own experience. So it's a kind of sharing of experience. So here you see an example. This is on an Android smartphone with NFC, where the system says carefully lift the metal strip, be cautious not to break the plastic and so on. Now pull carefully this, and then you can go on. And again, it shows how you have to do this. Now not through your classes, but simply on the smartphone. So it's a little bit simpler technology. The recognition, of course, is very precise because we have the NFC chips going on. And as I said, you can share the experience in case retrieval with your colleagues. So the idea here, we call it tutorial droid, is that the engineer, maybe on a desktop computer, generates the first draft of the computer, of the tutorial, but then in the field with a mobile Android device, the field technician is first logged what he is doing. We have a tutorial player, but he can also augment this tutorial with his own experience. So after a while, and we checked this out in various tests, the tutorial becomes even more practical because a lot of special experience of the field technicians goes into the tutorial. So this is the workflow and the life cycle of the tutorial. So first, maybe there is no tutorial available. Then an engineer who knows the machine generates the first draft. Then the field technicians are actually using this with their cell phone and are augmenting and commenting on the tutorial, so they add additional experience-based knowledge. Maybe the engineer checks and revises the tutorial again. He has a special tutorial editor, and then maybe edit the tutorial again. What this means is that we have both on the smartphone and on the engineer version, we have a tutorial editor, and it's very easy in the field to add comments and special tips for your colleagues how to repair, to install, or maybe exchange parts of such a machine. So this is also a very powerful and quite inexpensive approach in the factory of the future. Now, at the end of my talk, I would even be a little bit more aggressive. What I showed you today is technology which we are now rolling out. Actually, we work together with companies like Bosch, Daimler. Just last week we got a new project in the Industry 4.0 project getting launched, where we work together also with BMW. So all these manufacturing companies are now very keen. They talk about retrofitting their current production to the Industry 4.0 standard over the next years. So this is something which is not science fiction, but will happen in the next 5 years. A lot of money is going into this, and I'm pretty sure that if we meet again in 3 or 4 years, this is a reality, not on our living lab, but in many German factories. Now I will show you two things which are very exciting, which also come from our lab, but which are a little bit even more futuristic. As I said, and this is then also at the end of this talk, the idea of cyber-physical systems can also be used not only to be the object of the learning, but even the learning mechanism itself is in the cyber-physical system. And this was my idea. I worked for many years about this idea of so-called anthropomorphic objects. Because if you have a smart product today, you say you can download software and so on, that's fine. Even maybe this smart product can interact with you. But I had the impression that for many contexts, it's even better to scale up this idea to a real, like a human being, so that you can talk and interact with such an object as if it is a human being, and this is called anthropomorphic objects. And this is a little bit strange application. It's assembling a cocktail shaker, but also training you how to shake a certain cocktail. If you want to prepare a good cocktail at home or as a professional barkeeper, you better learn this. And what does this mean? This means that the device itself, you see certain parts here, talks to you and criticizes you and gives you the tutorial. Let's see how this works. It has a bit of Mickey Mouse voice.
Hello, friend. Great you are here. Please help to make this cocktail, okay? Do you like Machida di Coco? I like. Let's put it in. Some cachaça. A cream of coconut, condensed milk, and crushed ice. Finish.
This is all done on this hardware itself. So the shaker has speech production, as you hear.
Hey, stop! Everything will come out. Close me.
Close me. It has many sensors. It can observe what you do with it, yeah, when you shake it. You see, it has a complex dialogue engine inside. This is all running on this small hardware in the cocktail shaker. You see now you pull some coconut cream into the shaker. Now when you shake, it checks even the shaking style. This is very important, you know, when you learn about shaking. So it's really the physical interaction.
Can't you do better than that?
Can you not better than that? You should shake in another way, yeah? Now
here we go!
Now it likes it, so it really can track your behavior.
Jump from bottom to the top and back again.
And you see, it's anthropomorphic because the object is talking to you and giving you the instruction, and people really liked it. We tested it with a lot of students. It has about 10 different recipes. So remember the Russian, I don't drink a lot of cocktails, I'm not a specialist, but Pina Colada and the Russian white, I think it's called Russian white. It has these recipes, and there are different shaking styles for the recipes. What I wanted to show here is that this is even a further step. We talked in the factory, we have such cyber-physical systems, but this is a little bit more. You can imagine maybe in the factory of the future that even when you repair, the thing says, oh, don't squeeze me, this is completely wrong. Oops, please do it the other way. You do the screwing in the wrong way, this hurts me. Or I think this anthropomorphic behavior is very strong, a very good indicator for most humans to behave in the correct way, because you have the more kind of social relationship between you and the object. Now the last point, and this would be very nice if you would have it already running here right away. This was done, I was involved in a big European project called AMI. It was a very successful project together with the University of Edinburgh and in Switzerland, Lausanne. And what we did here is speech understanding, and this brings me back to my starting topic, computational linguistic speech, where the following is being done. From the learning point of view, I think excellent idea. It's learning technology which allows the student, during hearing a lecture like here, yeah, face to face, to retrieve automatically from the voice input additional material which is tailored to the individual student. So if you have if the system has a user model and knows that a lot of terms which appear in the lecture about, let's say, software engineering, and you know the student is not very strong in the background knowledge of software engineering, and the lecture is using terms like, here I use the term cyber-physical system, maybe some of you haven't heard it before, then what the system is doing is in the background retrieving in Wikipedia and other on the internet stuff which is displayed during the lecture. Let me show it. It's incremental speech understanding on the basis of the lecturer.
Collection will return us an iterator object, and the iterator object allows us to iterate through the objects in our collection by using the method hasNext to see if there is a next object to come, and the method next to get the next object from the iterator. Okay, so we've seen a number of ways to loop over or iterate over a collection. The for each loop is the simplest and easiest way of doing it.
This is a professor
you should always use
with
the
a Scottish accent, as you imagine in Edinburgh, teaching a lecture about software engineering, in this case about iterator objects in Java. It's actually a Java class.
You might use a while loop if you want to stop
when certain keywords appear, the system in the background would go to the internet, looking, what are the deficiencies of this single student watching or hearing this lecture in the classroom and giving background information.
And an iterator object, again, you can use an iterator object if you want to stop partway through. And iterators are sometimes needed where with some collection classes don't provide index
So what you see here is the transcript. It's incremental speech recognition. And what you see here is what the system retrieves in additional personalized information. So every single student here or the audience can get a specific other information, which this idea of the talk, situated learning, I think becomes again a reality in a very practical case. Again, technology which we developed at DFKI together, as I said, with the University of Edinburgh, which has also a very good group in this respect. Let me conclude. Situated learning and industrial assistance systems are, in my view, a key component of the fourth industrial revolution in what we call Industry 4.0 program. I showed that augmented reality tutorials based on markerless tracking of automatic video analysis of workflows allows a fast and very inexpensive production of learning material for smart factories. Third, as an alternative, NFC-enabled tracking of workflows with smartphones and crowdsourcing, so asking a lot of your co-workers to augment the tutorial by case-based tutorials are a practical way for learning content creation. And finally, I think that incremental speech understanding and tangible interfaces in this anthropomorphic way, as I showed, offer completely new opportunities for situated learning technologies. That was my topic. Thank you very much for your attention.